Okay, the last type of problem we're going to look at is something called a combustion analysis problem. What happens in a combustion analysis is that you take a sample of an unknown substance, you burn it, you react it with excess oxygen, and in the process you create new compounds which can be collected and analyzed. What we do is we try to figure out how much of these products are produced, and based upon the law of conservation of mass, whatever we end up with had to have come from the original compound, and so we're able to figure that out, figure out what the original substance was. So what we're going to do is we are going to work through a problem here. The idea is that we take an unknown sample, we burn it, so this original sample is 0.658 grams. It contains carbon, hydrogen, and oxygen. So they've told us what's in there. They burn it with oxygen, they react it with oxygen, and in the process we produce carbon dioxide and water. Well, the reason why we produced carbon dioxide was because the original substance had carbon in it. All of the carbon that was in the original substance is now in carbon dioxide if we collect it. And all of the hydrogen that was in the original substance is now in water. And then the oxygen is just the remaining mass, whatever was left. We cannot figure out how much oxygen was in there by looking at these two compounds because we added oxygen when we burned it. So what we're going to do is we're going to work through this problem. It's actually quite long, and at one point you're going to realize, oh, we are finally at the empirical formula calculation that we did in the previous page. So we'll just go ahead and work through this now. So we end up producing 1.285 grams of carbon dioxide. And based upon the formula of carbon dioxide, we know that there's one carbon and two oxygens, which tells us that the mass of this compound is 44.01 grams per mole. The percentage of carbon in carbon dioxide is the 12.01 divided by the total mass of carbon dioxide times 100, and we find out that any sample of carbon dioxide, 27.29% of it is carbon. The reason why that's useful is, since we know that we produced 1.285 grams of carbon dioxide, and 27.29% of it is carbon, that means the carbon dioxide contains 0.351 grams of carbon. Well, that 0.351 grams of carbon in carbon dioxide is also the same amount of carbon that was in the original compound. We do the same thing for water. Two hydrogens times its molar mass, one oxygen. Its molar mass is 16. And the total molar mass of water is 18.016 grams per mole. The percentage of hydrogen is the mass of the hydrogen divided by the total mass, and for simplicity I'm leaving out a lot of my units here, and we get the 11.19%, which we actually already knew. And so if we go back to the fact that we had 0.658 grams of water produced, and we know that 11.19% of it is hydrogen, that means the hydrogen in the water is 0.0736 grams, which is in the water and the original compound. Well, Our original compound has carbon, hydrogen, and oxygen. The way we find the oxygen is to go back to the fact that we had 0.658 grams of the compound, and it contained 0.351 grams of carbon and 0.0736 grams of hydrogen, so the remainder must be the oxygen, and that's 0.233 grams. And we are finally at the point now where we are back to the original problem that we had on the previous page of finding the empirical formula. So what we do is we take each of these masses, the 0.351 grams of carbon, we convert it into moles, which was shown on the previous page, dividing by the molar mass, and we end up with 0.0292 moles of carbon. The hydrogen, the 0.0736 grams of hydrogen, when we convert it into moles using its molar mass, we end up with 0.0730 moles of hydrogen. And then the oxygen, 0.233 grams, converting just like we did, dividing by the molar mass, we end up with 0.0146 moles of oxygen. To find the molar ratio, you divide each of these by the smallest, so the 0.0146 moles was the smallest. And when you do that, this is 1, this is 5, and this is 2. And so the empirical formula, C2H5O. Well, the mass of this formula, 2 carbons, 12 each, that's 24. These are just approximate. Hydrogen, 1 apiece, is about another 5, and oxygen has a mass of 16. If you add those all up, you end up with an approximate mass of 45 grams per mole. And if we look back up at the top of the page, we'll see that this particular substance has a molar mass, an actual molecular mass of 90 grams per mole. So how does that compare to our empirical mass? Well, 90 grams per mole is twice that of our empirical formula. So that tells us that our actual chemical formula is twice that of our empirical formula. So we end up with C4H10O2. Every compound has a chemical formula, and the chemical formula determines its properties. It determines its identity. And so being able to identify what the chemical formula is going to be extremely important. So in this lesson we're going to take a look at how we determine the chemical formula of a compound. We're going to look at how we do calculations such as percent composition and how it's related to the law of definite proportions. And we're also going to do a more complex problem related to something called combustion analysis, where we'll use the analysis or the products of a combustion in order to analyze and to determine the composition of a compound. Before we get into any problems, we want to spend some time working on some of the terminology that we're going to use. A chemical formula is going to indicate the relative number of particles in a compound. It's going to tell us the ratio of these particles, something that we often refer to as the molar ratio. Now, a molecular compound is a substance that has 2 nonmetals bonded together, and when these atoms of these nonmetals bond together in some ratio, they form something called a molecule, which is a discrete unit. And so a good example of a molecule is the hydrogen chloride molecule, where you have 1 single hydrogen and 1 chlorine bonded together, and that molecule is separate from another molecule. Hydrogen chloride, the identity comes from the combination of these two. So when you see the formula HCl, that formula is representing the actual number of particles in there. So it's representing the discrete unit called a molecule. And it's showing you the exact number of atoms in that molecule. Well, not all substances, though, are molecular. A good example is an ionic compound, such as sodium chloride. So the NaCl, while it represents the number of particles in there as a ratio, it's not showing you a discrete unit. NaCl is not a single sodium and single chloride is not a single molecule. It's not separate. But instead you'll find these in a complex network called a crystal lattice, where you'll have a repeating pattern, and it's in a ratio of 1 sodium for every chloride. So the formula represents a ratio, or the simplest ratio, in a crystal lattice. The same thing holds true for network solids, which instead of being ionic, the atoms are bonded together covalently, such as in diamond, or silicon dioxide. And in this case, this is a better example where you have two different elements bonded together. The silicon and the oxygen are bonded together in a 1:2 ratio, but it's a complex network where this formula is representing the ratio. If I go back up and look at the molecular compounds, we already mentioned the hydrogen chloride. The hydrogen chloride molecule contains 1 hydrogen and 1 chlorine. That is the simplest ratio as well. It's a 1:1. You can have a molecule of H2O where you have 2 hydrogens to 1 oxygen, and this represents a discrete unit. And there are with that particular combination. And hydrogen peroxide would be a third molecule where you have 2 hydrogens and 2 oxygens bonded together. Now, this shows exactly what's in there. You can talk about a simplest ratio, however, and that is our empirical formula. So whatever formula we're talking about, whether it is a molecular substance, whether it's an ionic substance, when you express it as the simplest ratio, that is the empirical formula. For a molecular substance, we can simplify this down to a 1:1 ratio. But in the case of an ionic compound, since we're already reflecting the ratio in the crystal lattice, the empirical formula is already expressed by the molecular formula. It is the composition of the compound, and it's also how the particles that are arranged that determine the properties of a compound. These compounds are, their properties are going to be fixed because what makes water water is the fact that it's 2 hydrogens bonded with 1 oxygen in a certain arrangement. What makes glucose glucose is the fact that you have a certain number of carbons, hydrogen, oxygens bonded together in a particular arrangement, and that gives it its properties. But we know that water is H2O, and that cannot change. So what was found long before they even knew that it was a formula H2O that represented water was the fact that the composition of a compound was always fixed. It cannot change. The amount of hydrogen compared to oxygen in a compound of water or in water does not change, will not vary from sample to sample. So this is something referred to as the law of definite proportions. We often talk about the amount of hydrogen oxygen in terms of percentages. It is a mass percent. So if we look down at our example of water, it has been determined that by mass, water is 11.19% hydrogen, and this again is by mass. And the amount of oxygen is 88.81% by mass. And again, that doesn't change. If we were to look at a totally different compound, if we were to look at hydrogen peroxide, which is has the exact same component elements, hydrogen and oxygen, We find out, though, that hydrogen peroxide is 5.93% hydrogen by mass and 94.07% oxygen by mass. And when you look at these, it doesn't look like there's much relationship between them. Obviously, there's more oxygen in the hydrogen peroxide than in the water. But what we can do is, if we were to get a sample of hydrogen and a sample of hydrogen peroxide, so two different compounds, and we got just the right amount of each. And what I mean by the right amount of each is that if I got so much water and so much hydrogen peroxide so that the two had the same amount of one of the elements. So here's what I mean. Let's say that we have a sample of water, a 50-gram sample of H2O. Well, if we were to take 11.19% of hydrogen, or rather if we were to take 11.19% of 50, we find out that that means we have 5.60 approximately grams of hydrogen in our water. Well, I've already done the math, but I have figured out that we would need to have a total of 94.35 grams of hydrogen peroxide. And that would also give us 5.0 grams of hydrogen. So you need more hydrogen peroxide to have the same mass of hydrogen. Well, just by taking the differences here, you'll find out that you need that means you have 44.4 grams of oxygen. And in this one, we have 88.76 grams of oxygen. Now again, these were using a specific, or this was using a calculation where I went through and used the percentages to find these amounts. And the interesting thing about this is that for the same amount of hydrogen, take a look at the amounts of oxygen. Now, it may not be too surprising to us because we know what hydrogen peroxide is, but before they knew what the formulas were, they were surprised to find out that, hey, there's actually twice as much oxygen in this other compound. It doesn't surprise us because since we now know the formula, we see that in the formula itself, if you have the same amount of hydrogen, the one compound has twice as much oxygen. So the law of multiple proportions states that if you have two different compounds with the same amount of one of the elements, the other element must be related by some small whole number ratio. What's the reason for this? Well, it goes back to the formula. The reason is the same as to why we have these subscript numbers here. We're expressing the number of atoms. There's these things called atoms, and you cannot have a fraction of an atom. So if you're either going to have in a compound one oxygen, if you have a different one, you're going to have two or three. You have to have some whole number multiple because you cannot have a fraction. So this was something called the law of multiple proportions, and it led to their ideas of what was or what was soon to be referred to as these small subatomic, or these particles referred to as atoms. In order to keep this lesson somewhat short, I'm going to hopefully breeze through a couple examples of some calculations that you're going to run into when we're talking about molecular formulas. We're going to look at how we determine empirical formulas and molecular formulas from masses or percentages that are given to us. So what we're going to do is we're going to look at an example of a substance that is found to be composed of carbon, hydrogen, and oxygen. And percentage-wise, this unknown substance is 40% carbon, it is 6.72% hydrogen, and it is 53.29% oxygen. So if we had 100 grams of this sample, we could take those percentages and know that in that 100 grams we would have 40 grams of carbon, 6.72 grams of hydrogen, and 53.29 grams of oxygen, because we know the percentages. There doesn't seem to be a nice relationship between those, and the reason for that is because we're talking about mass. But if instead we talk about the number of particles, and the way we talk about number of particles is to convert these into something called moles, which are just groups of particles. So if I have 40 grams of carbon, I know that from the periodic table that 12.01 grams of carbon can be found in 1 mole of these carbon particles, and that means that I have 3.31 moles of carbon. If I do the same thing for hydrogen, 6.72 grams of hydrogen, and I convert it into moles using its molecular weight, its molar mass from the periodic table. Then we can find the number of moles of hydrogen, and for oxygen, the molar mass of oxygen is 16 grams per 1 mole. And the numbers, while they still don't look great, when you look at them in terms of the relationship with each other, you see a pattern. The moles of carbon and oxygen happen to be the same, and hydrogen looks to be about double. Well, what we're interested in is the molar ratio. So perhaps they won't always look this nice where we can just see it right from the beginning, but what you do is, whichever one is the smallest number, you divide each of these number of moles by the smallest. And that should give us a whole number ratio. And the whole number ratio is the ratio of moles. And the ratio of moles is in fact a formula. Now this process here, when we divide by the smallest, it gives us the simplest ratio. And if we are finding the simplest ratio, that means that this is the empirical formula. With an additional piece of information, if we knew what the actual mass of the molecule was, we could get the actual chemical formula. So 1 carbon, 2 hydrogens, and 1 oxygen. A rough quick calculation is going to tell us that the mass of this formula is 30 grams per mole. 12, another 2, and 16 add up to 30. If we were told that the actual molecular mass of this substance was 180 grams per mole, so this is the actual mass, what we're able to do is compare how does the actual mass compare to the empirical formula mass. A quick calculation shows that 180 divided by 30 means that this mass here is 6 times larger than the mass of this formula. So if the mass of the actual is 6 times larger, then that must mean that our formula is 6 times larger than the empirical formula. And that would make that the actual formula, or the molecular formula.